So can they see the first slide?
Yeah, everything seems right now.
Okay. So this is a relatively simple case. All of this is nothing more than, this is just one MOSFET, this is a second MOSFET, this is a push-pull application. This is a transformer, and this is a particular load that I'm going to explain. So we have a 50%. I mean, we're going to see the LT spice just in a minute, but this is pretty much a 50%, you know, turning on this node and 50% turning on this node. And then there is, this is actually a transducer load. This is actually an RLC of sorts, but this is a Van Dyke model of a ultrasonic transducer. And this is a pulse driving application, essentially. Now, yeah, so let's take a look in the LT spice here that we have run. All right, let's run it again. Just 1 second. Okay, so we are plotting the output voltage, as you'll see here in a minute, for a few cases. Now the cases are, we are stepping this parameter, this RAC parameter. And well, as everybody has seen, I mean, this is the magnetizing inductance, the secondary inductance. It's nothing very fancy. I mean, this is just a step-up transformer, 1:16 ratio. So we have 12 volts here, and here we have 350, 400 volts. But the point here is that in the beginning, this is an unknown element. This RAC is supposed to be simulating the total losses of the transformer, essentially. Why do we call it RAC and not R total is a good question, but you can, for clarity, this is going to be the copper losses of the entire transformer. But the point, the webinar is about how can we know this value before we even design the transformer, right? Maybe you're gonna produce, you know, a very good design with minimal losses. So this RAC is gonna be minimum. Maybe you have designed something that has very high losses. So this is gonna be a higher value. So all I'm doing is stepping this parameter from 10 milliohms to 500 milliohms. And we have the output voltage right here, which is essentially, you know, your classic RLC circuits for those 4 conditions. Now, I started off the design of this transformer with the first case. The first case was, let's assume that this is a resistor that has, well, we can switch back. Let's make it simple. We can switch back to the second slide. And let's start off with this one, like the minimum resistance, which is like 10 milliohms. And this could, well, essentially, this might be similar to the DC copper losses, right? If you measure the primary and the secondary and you reflect all of the resistances back to the primary, it is going to be, well, certainly above 10 milliohms. So this is like our starting point into Frenetic Online, because we will design this transformer, as you will see, as a custom design, going here, starting up a custom design in Frenetic Online. And this is the operating condition 1. I have exported from LT Spice the CSV for this resistor to be 0.01 to get the waveforms and then start the actual design. By the way, I'm gonna take questions in the end from everyone. So if you have a question, just put in your question right now, and I'll switch back to it. No worries. So the first part is getting the waveforms, as everybody is aware of. And then we can go into the core section where I've selected an E30 core. This is like a small, relatively small pulse transformer, nothing very fancy, like 100 millihenries of inductance. AC flux win is a safe number, core losses are minimal. And if we go to the windings, primary and secondary is just round wire, Why? Because we don't really care about the performance, the thermal performance of the part, because in reality, in this application, the transformer is operating 7% of the time. Like the duty cycle, it's pulsing for 200 milliseconds and it turns off for 3 seconds. So even though we have high losses, we don't care that much because the effective duty cycle is going to bring those losses from 13 watts or 15 watts down to close to 1 watt, essentially. So we don't care about the temperature issues. But what we do care about is the total resistance of the part. Here, simulating that, we have the RAC, which is again the total resistance for this condition at 150 milliohm. So all I did, if I go back to the slides, is iterate back and forth between LT-Spice and Frenetic simulator. So we started off in LT-Spice with 10 milliohms. We simulated one operating condition with, well, I had an E30 core. I started off with a round wire, nothing very fancy with it. Oops, going back. And we have an RAC of 0.16 ohms, and then went back to the LT-Spice with this, and again to the Frenetic simulator with a different CSV file, you know, going back and forth. As you see, from the second iterations, I have the correct number. Actually, from the first one, is pretty close. So that tells us that essentially this ringing that is happening here isn't affecting the power losses of the transformer that much. So we have, from the first iteration, we have a correct number. Now, for the rest of the operation, this resistant is controlling the output, the effective output waveform, which is critical. I mean, the overdamped case is something like 200 volts, as we will see. In the undamped case is like 400 volts, which plays a huge difference, a huge role in the driving of the load. As well, as you see here, we have two frequencies. One frequency is the driving frequency at 39 kilohertz. Okay, and at 39 kilohertz, by the way, this LC is circuited. So we have a C1 with a load, and effectively we have the LR, which is the leakage inductance, the total reflected to the primary leakage inductance, which is ringing here. This is the F ring. I didn't mention it here, but this is close to something like 400 kilohertz. And this is pretty fixed, as we will see. Yeah, so going back and forth between LT-Spice and Frenetic simulator, we get the RAC, we go back to the LT-Spice, we run the simulation again, produce new waveforms for the currents and the voltages of the transformer, going to simulator. I mean, this takes like 5 minutes to do so. And that was a big part of this exercise. How can you predict, you know, where to begin with, and is it iterating to a stable solution or not? And reality is that it is, because the dependent on this on the ringing. That's essentially the solution. And yeah, we have the simulation versus reality here as a reality check, let's say. And this is the LT spice with a peak and the flat case. Let's say this is the point of the flat. And this is the actual oscilloscope, because there was a circuit here that was tested. And this and the important part is the number of oscillations. If you see 1, 2, let's say 3 oscillation, and here we have 3 oscillation at the same frequency. So that tells us that we got the RAC part right, because this controls the number of. So we're spot on here. And this is the transformer that was built and measured. Some comments here that I have. And there is actually a part here that I noticed when I was measuring it, that we have more oscillations on the lower half than in the upper part, and the only and the frequency is the same, by the way. So the problem isn't, you know, a discrepancy in the inductance. The LC part is the same because the frequency is the same. The only different part is the RAC, which in this case is different in this period rather than in that period. This is because of the geometry in the transformer. So the two primaries don't exactly behave the same as don't experience the same losses, driving losses. So one of the two has lower power losses than the other one, which is translating into one, you know, when this is conducting, the RAC has a number. When the other one is conducting, the RAC has a different number. Okay, we were not that interested in this, in these details. So this is very detailed, but that's why this is happening here in this case. This is pretty much it. That was something that I found out and thought that it would be interesting to share with you guys. I'm not sure if we have a question, or you want me to go back into something. We have a question. What does RLC load represent in real world? L3 is 47 milliamps in particular. L3, it's millihenries. All right. So the RLC in this case, let's go back. In this case, it was a transducer, an ultrasonic transducer. You know, when we have the PCBs and we want to clean them, you put them in a bath, like an ultrasonic bath. If you take this device apart, it has ultrasonic transducers on the bottom. So piezo mechanical elements, and the way that you can simulate those is like this. They have a resonant frequency and they have a stable capacitance here. It's a complex model. I mean, people have a career on the modeling of that, but essentially that was this particular case. But you can think of it like, okay, there is a capacitive, we have a capacitive load, and then we have inductance in series that might be parasitic, or it might be actual leads, you know, wires. This transducer, for example, has long wires in the application that I have in mind, but we didn't care that much because the effective inductance here is like 47 millihenries. But in other case, it might be a driving scheme. You may have an LC, you know, and it's ringing. How can you simulate this ringing behavior? Because if I remove this resistor here, I remove the losses of the transformer. So this, whatever LC you have here is going to ring. It's going to have to be damped by the primary somehow. Either with clamping, yeah, there is some clamping here, but mainly the resistor here is a Zener clamp. So you will see the oscillation and, you know, a flat top maybe. In this case, you know, this was not working in this case deliberately for you to see the effect of the RAC, but essentially this is how you would, you know, model it properly. You have to put the losses of the transformer transformer somewhere. In this case, yeah, it was forming an RLC, so those waveforms could be explained in detail. Let's see. Yeah, this concludes this webinar. And the main thing that I want you to take from this is you should not forget the inductance part. You should not forget the total AC resistance in the circuit, because this can make a difference. And this webinar is going to be available shortly after the slides for you to check, and the simulation part as well. Thank you for joining.